So for this, Unit 1, Worksheet 3, you were supposed to go through and answer these questions. And I hope this actually is going to work. My board has been acting up. My pens have been screwed up. Ugh. Anyway. Where was I? Oh, yeah. So mass. We have to compare the mass of A and B. So is A less than B? Is A greater than B? Or is A equal to B in mass? I hope when you look at this, you're thinking what I'm thinking, and that B has more mass. So that means A is less massive than B. And so we would say, oh boy, hold on, I gotta get this going. Oh man. So it would be like that. So A has less mass than B. Now, what's the reason? How do we know that? Hopefully you're looking at this and you're thinking, well, A doesn't have as many particles. So B has more particles. B has more particles than A. That's it. Remember, mass is about the particles. That's what mass is about. And so volume. How do these compare in volume? Well, I hope you can see that B is a whole lot bigger than A. And so, same sign here. B, and again, what's the reasoning? B is, oh, I hope, you know what? I wonder if my face down in the corner here, if that block part of that, I don't even know. So B is what? I would say B is bigger than A. Now, bigger, remember, volume is about size. It's about how much space something takes up. And so therefore, B being bigger than A means it has more volume. Has nothing to do with the space inside between the particles or anything. It has to do with how big is B. Now, some folks were saying that means you're looking at how massive it is. No, mass is this. Mass is the number of particles, okay? Volume is how big it is. Now, because its length and width are the same dimension, and the B is taller, you could say that with equal length and width, B having more height means it has more volume. You could say that, but that's a pretty complicated way of just saying that B is bigger than A. The bigger object has more volume. That's just what space, taking up space means. All right, so density, last comparison, density. How do A and B compare density-wise? Well, again, for density, you're looking at what? The spacing of the particles, okay? And how does that compare? Looks the same to me. I don't know why this camera gets bright and dark and bright and dark and bright and dark. Just like, I mean, no reason. Like what? Bright. I don't know why it does that. So, equal is what I would say. Equal. Now, how do you describe it? They have the same what? Same particle spacing. Same or equal particle spacing. That's what I would say. All right, the same or equal particle spacing between A and B. In other words, if we were to cut this picture off like this and you were only to see this part right here, not knowing how big either of them is, would you still be able to tell what the density is and compare the density? Yes, because it has to do with particle spacing. Can you compare their masses if they've been cut off like this? No, because we don't know how many particles they have. We only see parts of the objects. Can you compare their volumes like this with them cut off? No. But you can compare their spacing because the spacing can be seen regardless of if you can see the entire thing or not. I hope that makes sense. Now, this one only had us compare A and B and then A and C. We didn't compare B and C. So I threw those in over the side here so we could do a little comparison on those as well. So, mass. How does A and B? How do A and B compare with mass? Well, I hope it's pretty obvious that B has more mass than A, right? So B has more mass than A. And again, how do you know? B has more particles. B has more particles. How about A and C? Well, I hope you can clearly tell that C has more particles. You can count them, right? C has more particles. Now, how about, oops, what on earth is happening there? Why did that do? Oh, I know why that did that, because I'm not on the eraser right now. So how about over here with B versus C here? Well, how can you tell that? It's not so obvious. I mean, comparing A and B and A and C, that's pretty obvious which one has more mass. B and C, that's not as obvious. Like, we would have to actually count those out. If you didn't count them out, then let's see. Let's just do a quick count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 23. Or a bunch of little olives there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 27. Well, there you have it. All we had to do is count, and it tells us which ones got more mass. So which one has more mass? Clearly B does. So that's going to be like that. And again, how do you know? You would say because B has more particles than C. Perfect. All right, how about volume? How do A and B compare volume-wise? Hopefully you can see clearly that B has more volume than A. How do you know? B is what? Bigger than A. And I think I'm probably my face is probably cutting off that bottom part there. How about comparing A and C? A and C, how do they compare? Volume-wise, I hope you see that they are equal to each other. They are the same, what? Size. Again, size is space, which is how much volume they have. And finally now density. Compare A and B. Oh no, we didn't do B and C. Now, I hope you clearly can see, no pun intended, that B and C do not have the same volume. And that B's volume is bigger than C's. And again, how do we know that B's is bigger than C's? Because it's bigger, it's a bigger box. Takes up more space. It's larger. All right. Where was it? Oh yeah, density. So how does the density of A compare to B? A compared to B, A to B, A to B, A to B. I hope that you're seeing that and thinking that those are equal density. How do you know? Same particle spacing. Same particle spacing. Oh no, I've lost my E. Lost my E. How about A versus C? A to C. I hope that you can clearly tell that C is more dense than A. And how do we know? The particles, oops, no, I'll do this. C's particles are more tightly packed. More tightly packed, or closer together. You could say that. All right, C's particles are more tightly packed or closer together. That's how we know that C's density, C is more dense than A. A's particles are more spread out. You could say it that way, or that C's particles are packed in tighter. Either one. All right, so compare B and C density-wise. Well, if A and B are equal, and C is more dense than A, then C better be more dense than B, since B and A are the same. That only makes sense. So That means B is less dense than C. And again, how do you know? Because C's particles are more tightly packed. Hope that makes sense. Now let me get out of this one here. Let's go to page 2. All right, now for number 3 here, it says, when you look at these right here, it says assume the particles are uniformly distributed. What does that mean? That means they're spread out evenly. There's not like concentrated pockets here and there. So they are spread out evenly throughout each object, and particles with a larger size have a larger mass. So which one's more dense? Well, you can look at it a couple different ways. Density, remember, is the mass to volume ratio. It is the mass to volume ratio. Now, are these the same size? Do they have the same volume? Yes. Which one has more mass? E has more mass. Because even though they have the same number of particles, those particles are more massive. More massive particles means more mass total if it's the same number of particles, but these are more massive. That means for E, it's a mass to volume ratio like this where the mass is big. That means that's E. For F, we have a tiny little mass over a big volume. So in this case, this mass to volume ratio, that's going to be smaller. This mass to volume ratio, that's going to be bigger. The other thing you can think about is that how much space is there between these particles? Like, are these particles jammed in closer together than these? Yeah. So that makes this what? More dense. The particles are jammed in tighter. These are spread out more. E has to be more dense. So you can think of it in terms of the mass volume ratio, or you can think of it in terms of the spacing of the particles themselves. Either way. All right, now, number 4. Part A here. Now, what you have here is a graph with a substance A and a substance B. You have a 2-pan balance. And so what happens if you place equal masses of A and B in the 2 pans? This is like what we did in class. This graph looks a lot like the graph you had in the lab, where one line was steeper than the other line. And so substance A is kind of like which substance in the lab? I hope you're thinking aluminum, because it was the steeper line. And this line is kind of representing what from the lab? I hope you're thinking PVC, because that was the lower line in the lab. So if you put equal masses of each of those in the pans, what's going to happen? They're going to balance. Now, the thing about it, though, is that those pieces look like this. They're not the same size, okay? They are not the same size. The little one, aluminum. The big one, PVC. But they would balance perfectly, and they did balance perfectly, and I showed you that in class. I put those on the balance, and they were perfectly balanced. But they weren't the same size. I hope you see again that this is like substance A. This would be like substance B. Next question is, what if you put equal volumes of A and B in the 2 pans? Well, that would be like having these 2 pieces. These 2 pieces are equal volumes, if you see there. So those are equal volumes right there. Same size, right? Equal volume, taking up the same amount of space, but will they have the same mass? Answer, no. They cannot have the same mass because they have the same size, and they're not the same density, right? So if you put these 2 on a pan, what's going to happen? The aluminum is going to outweigh the, I forgot what it was, PVC. More mass in aluminum because we said it was more dense. There's more mass shoved into the same amount of space. Now, question B, you're supposed to find the slope of these lines, all right? So let me work that out real quick. Now, because they both look like they hit the origin pretty perfectly, I'm just going to use the origin as one of my places. And what on earth? They just switched to the, oh no. What? Oh boy. Am I pen? what is happening here? Why is this not? Oh, whew. I didn't know what happened, but oh no. Why is it? Whew. This is not responding very well. Why is this not working? Oh, I got a bad feeling about this. Well, this may be a problem. Okay, maybe this will work. Okay, good. Oh, that's not what I wanted. I want this space right here. This one right here. That looks like a pretty good grid intersection. I'm going to drop it down like this. I'm going to take this across and begin. Again, because it's at the origin, I think that's a pretty good place to use if the line hits the origin. So I'm going to say that my rise right here goes from 0 down here up to 30. So that's 30 grams of rise. And my run goes from 0 over to 60. So that is 60 mLs of run, which means then, if I scroll here, that's going to be 30 grams of rise over, this is for B, over 60 mLs of run. That's 0.5 grams for every ml. Now, how about for A? Well, let's look at A. Well, let me find a good place to use for A. Oh my gosh, I don't really see one. Well, this is about it right here. That's pretty good. So I'll take that one down here and then across. And so that, for A, goes up to, so that's 40 grams starting at 0. And this one goes over to here, which is actually hard to see since the 60 is there. Move that over. That looks like 25. So that is 25 mLs. So now for A, I have, for A, I have 40 grams, 40 grams over 25 mLs, which is like 1.6 grams for every ml. Now it says, state the physical meaning of the slope for each substance. Well, this is telling us that for substance B, there's a half a gram for every ml of volume, 0.5 grams for each ml. For A, substance A, it's telling us that there's 1.6 grams for each ml, which remember is the same size as a centimeter cubed. So what are these slopes? They are the densities, all right? These slopes are the densities of these two substances. Substance A is 1.6-ish, 1.5, 1.6, and B is 0.5. Now, these next couple questions, they can be really confusing, okay? So just bear with me on these. I'm hopefully going to try to make sense of them. Now, oh gosh, I got to try to... I'm going to get rid of this stuff just so it's cleaner on the graph. Now, they ask, if you put 10 mLs of A in one balanced pan, how much mass of B would you need in the other pan to make it balance? Now, folks, what does a balance compare? When you're looking at this two-pan balance, what kind of quantity, what kind of measurement does it compare? Does it compare the volumes of the thing, the densities of the thing, or the masses of the things? The masses. A balance compares mass. But what did they tell us? They said if you put 10 mLs of A, what's mLs? That's a volume. They gave us a volume, but then they said how much mass of B would you need? Well, you need exactly the same amount of mass as what that much A has, but we don't know how much mass A has if it's 10 mLs big. So they gave us a volume, but they want a mass. So we have to look at the graph then and figure out, okay, what is this? So we go to 10 mLs like this. Go to 10 mLs. We go up and up and up and up and up until we hit the line. Then we hang a left, and we're right there. Ooh, I'm not even at the right. We're right there. So how much is that, do you think? Well, it looks like about 16 grams to me. It looks like 10 mLs of A is 16 grams. Now, how much mass of B do you need then? How much mass of B do you need to balance 16 grams of A? You need 16 grams of B. You need 16 grams of B to balance 16 grams of A. So kind of a weird question. So they gave you a volume of A, but they want to know how much mass of B you will need. Now, question D is even weirder. It says, if you put 35 mLs of B in one balanced pan, what volume of A would you need in the other pan to make it balance? Again, what does a balance compare? Mass, not volume. But they gave us a volume, and they're asking for a volume. So here's what I would do. Let's look at the graph at 35 mLs of B. So 35 mLs of B, let's look there. So scroll to the graph here. So 35 mLs is right here of B. And then I hang a left. Oh, now I got lines everywhere. So that right there looks really close to what I already had. So wait a minute here. How much mass does 35 mLs of B have? Looks like about 16 grams, about the same as what I had before. So how much volume of A do I need for that? Well, it looks like 10 mLs, because look at, now follow what I'm saying here. This is what I hope you're getting out of this, is that these two substances, A and B, if we want them to have the same mass, so if we want them to both be 16 grams right here, 16 grams, what can't they be? If they have the same mass, they cannot be the same what? Size. They cannot be the same size if they have the same mass, because they're not the same what? Density. They're not the same density. So they can't have the same size if they have equal amounts of particles. So that's what you need to get here. If B has 35 mLs and A has 10 mLs, that's going to give you an equal mass of 16 grams each. So weird questions. I wouldn't ask questions that are quite like this. I wouldn't ask questions quite like this. I might say, hey, if you have 16 grams of both A and B, which one's a bigger piece? Like that might be a question I would ask. If you have 16 grams of substance A and 16 grams of substance B, which one of those is going to be a bigger chunk? And you would look at the graph here and you'd say, okay, that's 10 mLs for A. Okay, that's 35 mLs for B. So obviously the chunk of B is going to be bigger because it's less dense. So you need a bigger piece of it to equal the same mass. That might be a question I would ask. But the way this is all worded is just kind of confusing. Now, finally, let's get done with that. Oh, let's see. Water has a density of 1 gram per ml. Water has a density of 1 gram per ml. Sketch the line representing water on the graph in figure 4. Okay, now, density of 1. Let me get this other stuff off here. So they're saying if you were to sketch a line for water on here, where would it be? Well, remember, we found out that this one's 0.5. That's 0.5 grams per ml. This is 1.6 grams or 1.5 grams, whatever you got, per ml. Where's 1? Well, a slope of 1 would be like going 10 over, 10 up. Yeah? 20 over, 20 up. 30 over, 30 up. 40 over, 40 up. Right? That's a 1-to-1, right? If your rise and your run are equal, that's a slope of 1. Up 10 over 20. Up 10 over 10. Up 20 over 20. Up 50 over 50. So where's that line going to be? I hope you were already thinking this. Maybe you already had it sketched. I don't know. But I hope you were thinking that it was going to be right smack dab through the middle of the graph like that. Like right between 0.5 and 1.5. And my line's not exactly where it should be, but it's a little curvy. But it should be in between these two. That's what that means. Okay, moving on. Now, you did not have to answer the next question, but we started talking about the next question in class. So I'm going to hopefully wrap this video up pretty soon. I know it's getting long. Now, the next question is determine whether substance A and B will sink or float if placed in a bucket of water. Is A going to sink or float? Well, A's density, remember, A's density is 1.6 grams for every ml. Water's density is 1 gram for every ml. And B's density is 0.5 gram for every ml. So, what's A going to do? A is going to sink, B is going to float. How do we know? Because things that are less dense than water float in water. Things that are more dense than water sink in water. So my question is this: what do you do in water? Do you sink or do you float? Hopefully, we'll see. I can do a little of each. I can sink if I want, but I can also float if I want, barely. And what's the difference? Like, how can I change whether I sink or float? By using these lungs here. When I take a deep breath, my chest cavity does what? It expands, which means what changes? What changes? That makes my volume get bigger. Let's just use some numbers here. Let's just say my mass is 10 and my volume is 10. If my mass is, I didn't put units of measure there because I don't even care what those are at this point. It's just a mass of 10 and a volume of 10. That means my density is what? 1. But what if I want to float? Then my density needs to be less than 1. So what do? I take a deep breath of air, which makes my chest cavity get bigger, which means my volume does what? It goes up. So that means maybe this goes up to 11 or 12. Now 10 divided by 11 or 10 divided by 12, that's less than 1. I float. But what happens when I let all the air out of my lungs? My chest cavity shrinks. My volume goes down. It decreases, which means it's no longer 11. Now it's down to maybe 9. What's 10 divided by 9? More than 1, which means now I'm more dense than water and I will sink. So I can change my volume slightly with my lungs by expanding or contracting my chest cavity. I can change my volume enough to alter my density so that I can sink if I want, or I can float if I want. So we had that conversation in class as well. Last thing, and then I'll let you go. So this whole list here, a bunch of different substances. And if you look at this, 2.7 for aluminum, that's the one we did in class. And that, in terms of metals, that is not dense at all. That is the least dense of all the metals. Now, titanium, it's pretty low compared to the rest of them as well. More dense than aluminum for sure, but it's also stronger and more durable than aluminum. And so then zinc, tin, iron, these are all on the periodic table. And then you got gold down there at 19.3. Holy mackerel, that is dense. Now, this says to sketch the graph. I'm not going to have you do this. I just want to show you how you think this through. Sketch a graph of mass versus volume for titanium, copper, and mercury. Well, let's just look at titanium real quick. Well, no, let's look at copper because I think it's going to be an easier number to use. I'm just going to say that copper's density is about 9. So if you look here, it's 8.96. Let's just round it to 9, okay? If it's 9 for copper, how do you sketch a line on this graph that represents copper when we don't have any copper data? Like in the lab, you measured aluminum Okay, you measured 4 different cylinders, the masses and the volumes of 4 different cylinders, and then you plotted the points and you made a graph. All we have for copper is this right here. That's all we have. We know that copper is 9 grams for every 1 ml. That's what we know. 9 grams for every 1 ml. That's a mass to volume ratio. Is this a data point? Could I go over 1 and up 9 and put a point for copper? Over 1 and up 9. That's going to be about right here, just shy of the 10 mark. Okay, so that's a 9 to 1, right? How about an 18 to 1? I mean 18 to 2, excuse me. How about 18 grams to 2 mLs? Is that still a 9 to 1 ratio? Is that still a 9? So if we have 2 mLs of copper, that's not just going to be 9 grams, it's going to be 18 grams. So can I go to the graph here and go over 2 and up 18? You betcha. Over 2, up 18, which is going to be about, right there, shy of 20. I wonder what happens if you go over another one. So if you add another ml of copper, then you're up to what? Oh, I just erased it. If I go over another ml, now we're up to 27 grams. Which means I go over to the third ml here. Let's see, 10, 20, that's 30. So that'd be about 27 right there like that. And then what if I go over another one? I feel like DJ Khaled. And another one. So I go up 4 mLs. And add another 9. So now we're up to 36 grams. So now I got to go over here, go over 4, and then go up 10, 20, 30, and then 6 is just over halfway. So do you see what's happening here? Do you see that I'm actually creating a line like so for copper? I'm creating copper's line by making up data, because if I know that it's a 9 to 1, it's always going to be a 9 to 1. And so I can go over 1, up 9, over 1, and up another 9, over 1, up another 9, over 1, up another 9, over 1, up another 9, until I get a whole line that's created. And again, the whole point of this exercise is to see that these slopes, these slopes are the density. And these densities are what you found for aluminum and PVC in the lab by finding the slopes of those lines. So see, in the lab, you had the line, and then you found the slope. Now you've been given the slopes, and you can work backward then and create the line by knowing that it's over 1, up however many. It could be 2.7, it could be 4.5, it could be 9 like we're doing now, it could be 19.3. Depending on what substance you're looking at, it has its own unique ratio of mass to volume, and you can recreate that data just by saying, if I add another ml and another one and another one, and you just keep making the data. I hope that this kind of makes sense. I didn't want you to necessarily have to do that, because most students get really confused as to how to even start. But I hope now you see, and it kind of makes sense, that these densities are the data. Over 1, up 9, over 1, up 9, over 1, up 9. It's a 9 to 1 ratio for copper. I think that's all I wanted to say about that. So here's what's going to happen. The next block when you come in after this, I'm going to do one more little example with you and ask you a few questions to review, and then you're going to take the test on mass, volume, and density. So you better know what mass means and how to describe it, and draw particle diagrams that demonstrate it. You better know what the law of conservation of mass is, which we had talked about. You better know what volume is, and about centimeters cubed in mLs and how they're the same thing. You better know what density is and how to describe it, that it is the slope of a mass volume graph, and it is the ratio of mass to volume. So all that stuff you gotta know for the test on Thursday or Friday, depending on which block you're in. So I think that's it. Hopefully this video worked out, and hopefully it helped. We'll talk to you later. Take care.